Okay, so couple of announcements. So Homework D2 has been out there. It is technically due today, but what we've done for this homework is just relax the late policy. So even though the due date is today, there's not going to be the 20% per day off. And so you can really turn it in anytime today or over the next 4 days. So basically you can use the availability date as sort of a de facto or effective due date. So that gives you a little extra time to work on the homework, but then there won't be any, you can't turn it in at all after that. And then because the solution set will become available right after the availability date closes. And then we did that so that you get a little extra time to work on it, but also get a chance to see the solution set before the upcoming midterm. So if you need additional help on there, the homework underneath the homework. So if you go to Unit D and go under the homework, then like indented under there, there's a number of different help resources, videos, additional documents, samples, etc. So make sure to check those out. It asks you to histogram. So a common issue that we get is that sometimes when you're generating random variates, I'll get students that just out of habit histogram kind of the wrong column. And so like, let's say you have done your random variates in an Excel spreadsheet, and down one column you put uniformly distributed random numbers between 0 and 1, and in the second column you've put your random variate samples. Well, if you histogram the first column, then you just get a uniform distribution. That's kind of boring. And so what we're really looking for is the histogram of the random variates of not the input but the output. So make sure that you histogram the output of your random variate generator, not the input to your random variate generator. And there was a question in the private chat that said, does that mean the due date would be on Saturday night? Off the top of my head, I don't want to do that calculation, but if you look at the availability date on Canvas, it tells you the due date. Just as a quick, looking at a calendar here on my other screen, today is the 29th. So I would assume that it would be due, that it would be due Saturday night. That is what I assume would be correct, but double check the Canvas. You should be able, even in the student view, to see what the availability is on that assignment. Whenever it disappears, that's the last time you can turn it in. But the goal, I think, was to make it so that you could do it as long as possible, but still get some weekend time to be able to see the solution set. So I believe I have it set timed so the solution set will go live Sunday, which means you won't be able to turn it in Sunday. So then you'll have Sunday and Monday to look over that solution set if you want additional help preparing for the midterm, where you will have to worry about random variate generation, random number generation. Okay, so about submission types, I mean, basically I just, the big things for this one is, make sure it's legible, make sure it's easy to follow and grade, and you will be generating thousands of replications. Those do not count as your solution. So the things I asked for are like, the histogram is your solution, the formulas are the solution. Don't submit like an Excel spreadsheet and expect the TA or the grader in this case, to go through and grade your 1,000 rows. We do ask you to upload that spreadsheet as part of the kind of like show your work spirit, but the actual deliverable that is the main thing that's graded are the summaries of those things. So, so again, we're not looking for the thousands of rows, although we do ask you to upload that. It's nice to have like a separate document that actually has your compact solutions in there. And if you're doing a little bit of math and you want to do handwriting for this submission, that's okay. Just make sure that it is clearly legible. And instead of uploading a bunch of images, like here's page 1, here's page 2, embed them in a Word document. So just take the same images that you might have scanned in and then put them in a Word doc. And what that does for us is it makes sure that Canvas renders them in the right size. Otherwise, sometimes we have to pan around images while grading, and it's really hard to grade. And it also makes sure it puts them in the right order. So, so ultimately, it's best to just upload that Word doc with things embedded into it, and then alongside that, as part of kind of a show your work, your Excel spreadsheet. Yeah, and there's a couple other minor notes here. There's now the Canvas activity F is available. This is meant to be a midterm practice. This is a little different than all the other Canvas activities. You can take it as many times as you like. It samples from questions from all the other ICAs, and I also added in a few others to help with things that haven't necessarily been tested over in those ICAs. And so again, that's meant to just get your mind going before the lecture F, which is on Thursday, which is our midterm review lecture. So lecture F, I do have slides prepared, but they're mainly just meant to kind of, I'm basically picked my greatest hit slides from all of the previous lectures and assembled them together in things that I think would be good to highlight as you go into thinking about the midterm. I'm perfectly happy just to take questions during that period as well. So the lecture F is really just there just in case there aren't questions. So try to think of things that you still would like some clarifications on, and that's what we can save for Thursday. Midterm. So there are additional solutions. If you go to the midterm module on Canvas, then you'll find that that's where the eventual midterm, because it's going to be given on Canvas, will be located. But there's also additional solution sets for prior year midterms and other resources that might be helpful. Because we're going to be doing this thing with Respondus Lockdown Browser, then soon this week, I'm going to put a little required practice assignment that'll be like a 1-question quiz on Canvas that you'll be required to use Respondus Lockdown Browser to do, and you'll have to do that before your midterm next week. And if you do it, you'll get like a tiny little fraction of midterm credit for it. And that by making that a due before the midterm, I'm hoping that works out any technical issues. And so I'll probably bug those of you who don't complete it quickly to say, oh, by the way, you haven't completed your practice exercise yet. You really should do this before the midterm because you don't want to be stuck on the midterm with technical issues. So the original date of fall break, I think, was like a week from next Tuesday, 2 weeks from today, something like that. So of course there isn't fall break this year. We've been encouraged to move all our class stuff forward to use that day as fall break to free up extra time in the last week so we can jam in more final exam and things like that. I don't want to do that because I think some of you might have assumed that you had fall break, and I also want to keep things as close to being in sync with lab as I can. And so I'm going to sort of continue as if we had fall break. And so with that in mind, it says fall break here, but even though we don't have fall break, that's what I mean. So the lecture period Thursday after fall break is going to be that midterm retake. So basically next week is going to be on Tuesday. And by the way, if you need a schedule for these things, I'm just going to pull this in. This is available on Canvas, this schedule that I've just pulled into the window here. And this is kind of a tentative schedule for how things go down in the lecture period here. So you can see that we're here, lecture E2, down here on September 29th, lab 6. Then we've got the midterm review on Thursday of this week. Then October 6th, that's when we have scheduled the midterm. We'll have another lecture, and then deciding what to do with that extra day there, but rather than moving everything up. And then we've got our midterm retake. And so the midterm retake is slotted here for October 15th, which is basically a week and a half after the midterm. So you'll take your midterm on the 6th, you'll have your scores and solutions available between the midterm and the midterm retake, and then you can decide whether you would like to take this retake or just take that day off, or you could skip the midterm and just decide to only take the midterm retake. The retake is going to be of similar length, similar difficulty, over the same sort of content, but it will be different questions than the midterm. So that's what's going on there. So that's the schedule. And this PDF is available under the course information on Canvas if you ever just want to need to sort of look ahead. So again, I still haven't quite figured out what to do with that day of spring break. I'm still contemplating doing what they're recommending us doing, like moving everything forward so that we free up some extra time during this final week. But I'd really like to avoid that. It just kind of ruins the schedule and makes it harder next semester where I have to undo all those changes. So so that's what's the kind of the schedule here. And that's, again, the mention here about the retake. Any questions about the midterm or the midterm retake? So I could go forward to my question slide here. Again, lots of resources available online. I'm pretty sure I have the 2018 midterm solution sets available online. Let me take a look at the 2019 ones as well, and I'll see if I can also make those available. And then, specific questions about the midterm. I haven't even made the midterm yet, so I don't know exactly everything that's going to be on it. I know sort of what content I want to be on it. So that's what we'll go over on Thursday. All right, so then carrying on through to content which may help you if you're still working on the homework. We have been talking about generating random variables for simulation. So the idea here, the vision that we have here is we come out of classes like 380 and 385 and we are loaded up with these distributions, and hopefully we pick up a couple more of these distributions. So right now they're very abstract. And so we're saying in the real world, there are small things about the real world that can be well modeled by these random variables. And so the idea is we choose random variables where we can to model aspects of the real world that would be inputs, variable inputs to our systems. You know, how long does it take for this machine to break? How long between people to arrive at this store? What is the distribution of demand that I'm going to get in my with my inventories as people bring their orders in, and so on and so forth. All these things are random variables that we just have to accept as given from the universe. You know, they come in and that's it. But then we, as operations researchers, can then develop systems which are robust to that variability, or generate other types of variability, or make use of that variability, and so on. And that's kind of what we do in simulation, is we take these input models down here, we push them through our kind of deterministic idea of process, and then we end up getting variation on the output, which is the generated from the variation on the input plus how we've reshaped it through the process we've engineered. And then we can do stats on these outputs and say, do these outputs look like what we want them to look like? And if not, how do we fix them? And so in order to get there, you need a way to generate these random variables. And so I've built a system that, say, is simulating this process that involves something that inspects an aircraft wing. And so I need to simulate that process that inspects the aircraft wing before I can put all the other puzzle pieces together. So this is like one Lego brick in my whole castle that I'm building. And in order to get that Lego brick to work, I need a simulation for those variable times to when this machine breaks. And so I've decided I want to make it an exponential distribution. So how the heck do I get an exponential distribution into my simulation, into my castle? So this is my brick. Where do I find that brick that I can assemble all those other bricks together to build this thing? So I want to draw samples from this exponential distribution. And so this is my PDF, my probability density function of the exponential distribution. So they would find that we would like to know what the area underneath that is to generate the CDF. And so that's just the accumulated area underneath that PDF. I get this nice concave shape here, this diminishing marginal returns, diminishing marginal probability is what we're seeing here. And so we'd like to say, well, then how do we draw from an exponential random variable? Well, if you have the CDF of an exponential random variable, you do an inverse. And so you basically can take random draws from random numbers from uniformly distributed from 0 to 1, and you push them in to the kind of wrong side of the CDF. And you so basically can invert the CDF. That's what you're doing on your homework. And then that allows you to take something that was uniformly spaced out and stretches it out so that you get a cluster of things that are closer like this, and a few of them that are out here. So most of the failures will be close to 0, but then there'll be a few that will be out here. And that is exactly what we've done here with this inverse transform. Is we've pushed this uniform random numbers into one side, and we've gotten rid of that uniformity. And that's kind of what we're learning to do during this lecture and what you're practicing on your homework. So that's where our motivation is coming from. So then the last time we said, well, how do we generate these inputs for this inverse transform? How do we generate these uniform random numbers from 0 to 1? All we have is a computer, and the computer, it isn't random, it's all deterministic. The best we can do is execute a deterministic mathematical function. So how can we find a deterministic mathematical function that generates randomness? And how do we do it in such a way that it's kind of a useful randomness? And by useful randomness, it needs to be started with a seed, where if I start with the same seed, I get the same random numbers, but if I start with a different seed, I get an independent string of random numbers. So now every seed kind of can be treated like an independent replication of my simulation of a factory floor. So I like these seeds to produce, to give me reproducibility within the sequence, but I want the sequence to itself, if I'm just staring at that individual sequence, to look like it's producing a bunch of independent random variables. And if I go across seeds, I want those sequences to look independent from all the other sequences, but I want to be able to generate the sequence over and over again if I start with the same seed over and over again. And so that's kind of our goals for this. And so in Excel, they kind of leave out the access to the seed thing. So unless you get into macro programming in Excel, if you're just using the rand function in Excel, then the timer is internally used as their seed. And that's why if you resave a spreadsheet over and over again, you get a different string of random numbers every time you save it. But in Arena, we get access to that seed. As in any good simulation platform, you should get access to the seed and be able to save that seed for your different replication runs. And so we haven't gotten to this quite yet in Arena, but you've already started using Arena. If you were to go into the elements panel and on the left-hand side, and then the seeds block, you can then add, they say, a seed, and then this, that will pop up a box that allows you to say for a certain stream identifier, you can choose whatever seed you want. And this allows you to force the seed. If you don't force the seed, there's a default value that Arena uses. And that's the reason why if you take all of your work from Lab 5, exit Arena, and reopen it and rerun it, you'll get exactly the same statistics out. And because a lot of people start noticing that and they say, Dr. Pavlic, Ted, what's the what's going on here? I thought this was supposed to be a stochastic simulation, and every time I rerun my sim, Arena gives me the same results out. And that's because when you start up Arena, it always by default in stream 10, which is the default stream, uses the same seed. You can change that seed, or you can tell Arena to do different things, and kind of this is a more advanced, and we'll get to this after a midterm, so that it does more intelligent things with that seed. But by default, it just uses the same seed. So every time you start Arena, if you run the same model in Arena, every time you open it up and hit run, you'll get exactly the same statistics out. So because it looks stochastic, but in the end, it's actually running the same deterministic sequence over and over and over again. So to give you an example of that, you now should have, now that you've done Lab 5 or been working on Lab 5, you are familiar with putting in triangular distributions. You're familiar with basically setting up parameters for these different distributions. Well, inside Arena, when you are ever asked for an expression for a random variable, it'll ask you for the parameters for that random variable. Like for a uniform, it'll say, what are the min, what are the max? But there is an optional parameter that you normally leave off, and it just assumes it's 10, but you can put whatever you want in there. And that allows you to say, for this aspect of my system, I'm going to use this random number stream, which uses this other seed. For this aspect of my system, I'm going to use a different random number stream with a different seed. So you can actually go through and even seed different parts of your system differently. And that kind of adds an even stronger kind of independence between them. And so these are all things that we can play with in Arena that we can't do in, say, Microsoft Excel. But this is getting a little more advanced, but I just want to try to get this idea of where these seeds come from. And I want you to get the idea of seeding, how that relates to the random number generation that you did in the last lecture. All right, so so just to see how many people are paying attention, so I listed here, like, these are sort of pictures of these two properties that I'm saying are the most important properties of random number generators. So up here, I'm saying that these are good and these are bad according to one property. And down here, I'm saying these are good and these are bad according to the different property. What are the two most important properties for a pseudo-random number generator? So in this case, you can just put it in the chat. So I'll just wait for a few answers to see how many people remember. What are the two absolutely most important features for a pseudo-random number generator? And I'm seeing some answers coming in. That's great. I'll wait for a couple more. And just to stress that although I've said there are desirable properties, as a lot of times I ask this on a midterm, and people will list the desirable properties of a pseudo-random number generator. Although there's desirable properties, there's also these required properties, and so these are the ones here. So it looks like everybody is coming up in the chat with either uniformity and independence or independence and uniformity, which are great. Great answers there. And those are the answers I was looking for. Those are the ones you should absolutely remember, the required properties for a pseudo-random number generator. Everything else, speed, memory, all that other stuff, is icing on the cake. That's great if you can get it, but you absolutely must have uniformity and independence. And so as an example, so up here, if you look, I've got a stream of, it's easy to look kind of at these bad numbers down here. If you at first glance, at a mile-high view, looking down at these numbers, they look like they're spread all over and they look perfectly fine and random. But if you kind of look more closely at it, you see that there are a bunch of them that are kind of colored in red here that are clumped around 0.2. And then there's another bunch of them that are clumped around 0.7. And a couple more that are just falling in kind of in between. But pretty much, if I were to take a histogram of these numbers, there would be a large peak around 0.2 and a second peak around 0.7, and only a couple in between. That is non-uniform, so that violates the uniformity property. So on a midterm, what I really like to do on midterms is, you can look back at our last couple of midterm samples, is I like to give you sample sequences from a pseudo-random number generator, and sequences that I designed so that if you're comfortable looking for uniformity and independence, they should pop right out as violating one of those two properties. And so, so this is kind of an example of that, where if you could look down at these numbers and you'd see that you saw a lot of numbers clumping together, then it probably is not uniform. So it'd violate that uniformity. If you did a chi-squared test or a Kolmogorov-Smirnov test, it probably would say not uniform. The other one is independence. And so down here, this is a good sequence here, and then down here, all I've done is sorted that sequence. So 2, 4, 6, 10, 11, you can see they're all just sorted but they're the exact same numbers. Both of these sequences have uniformity. They got that going for them. But the top sequence has independence too. I cannot predict the next number from knowing the previous number. But in this bottom sequence, after the first three numbers, I get the pattern. It's always increasing. So I know that when I see 0.11, I'm never going to get anything less than 0.11. So my next number is probably going to be higher than 0.11. And if I kind of notice that on average, these are like, oh, they're about 0.2 away from 0.02 away from each other. So I know that if I guess 0.02, I'm probably going to have a pretty good chance of getting the right number. It won't always be right, but it'll be a lot better than I get just by guessing totally randomly. So that lack of randomness you get by learning the pattern, violates that independence. Now, again, ultimately, pseudo-random number generators are not independent. They're also not that uniform. They're just determinate. They're just mathematical functions. So if you keep plugging in the output back into the input, you get a sequence which appears random, but of course it has a pattern. The hope is that that pattern repeats after such a huge long cycle that knowing a little bit of that pattern doesn't help you figure out where you are in the pattern. So uniformity and independence, those are the two things we're trying to approximate when we build pseudo-random number generators. And then if you have to think, what are the two tests we need to check for this property? And from that previous lecture, you should watch that. Uniformity, Kolmogorov-Smirnov test, if you have a small number of samples, and the chi-squared test. And then we're going to go over quick examples of those in a couple of slides here, just to make sure that you've seen those in front of you. So those are the two tests for uniformity. Kolmogorov-Smirnov test, which both of these tests, by the way, the chi-squared test and Kolmogorov-Smirnov test can test for other things too, like normality, etc. We are using them here to test for uniformity. The grader mentioned to me that a couple of people, when they use the Kolmogorov-Smirnov test on their prior homework, phrase their answers in terms of normality. And they probably did some Googling and you saw that the KS test is sometimes used to test for normality. It doesn't have to be used to test for normality. And the way we are using it here, it's actually to test for uniformity. And that's actually the more natural way to use the KS test. We will learn how to use the KS test to test for normality after the midterm. But for now, the KS test is what we use to test for uniformity, as in the chi-squared test. All right, so that's uniformity. Oh, and I'm sorry, a private question here. Why is the pattern bad? What does that mean? So I think, so the question here is, why is it bad to have a pattern? It's not the particular pattern that's bad, it's that the numbers are predictable. So if you can look at a string of what are supposed to be randomly generated numbers, if you can guess the pattern that's coming up, then that means that there is a lack of randomness in the numbers. And so we need kind of maximal randomness, which will mean that we need to, like, for example, if I want to faithful, so what we assume is like that aircraft wing example. We have this machine that checks the aircraft wing for cracks. If that machine fails after, say, a year of service. Now we know that on average, maybe they fail on average every 2 years, but this one was a particularly bad one. It failed after a year. That shouldn't give us information about the next machine we buy to replace it. And so if we buy a new machine, it might fail after 3 years. It might actually, we might have gotten lucky with that one. But if in simulation, if every time we get a machine that fails after a short period of time, they then draw a new machine in simulation that also then fails after just a slightly longer time, and a slightly longer time, that kind of is not realistic. So in reality, we assume that there is an independence to these events, so that the length of time until the failure of the machine is independent of the length of time to the failure of the previous machine. And so we need a way to simulate that independence, and that independence needs to come from somewhere, and it comes from this pseudo-random number generator. If we want to add dependence later, if we want to add a pattern later, we can do that ourselves as simulation programmers. But it's really hard to get rid of dependence. It is really easy to add it. So we need to start with independence and then gradually add independence as we need it. Does that help with the question? It's a private question was sent in the chat. So if that doesn't help, then let me know with a further question. But we just do not want the numbers to be predictable, and we want them to be uniformly distributed from 0 and 1. You give me those two properties, and I can generate any other random variate you want with any level of dependence you want, but I need to start with those two properties in order to do it. Okay. And if you need some more conceptual help, board games, I think, are a great example of this, is that you count on that die roll to give you a uniform distribution across the die, and you count on every roll of the die to be independent of every other roll of the die. Imagine how different board games would be if you could not count on those properties. That is what we do in simulation, is we basically build board games for money. And so instead of building them for entertainment, we're building them for operations research, but they operate on exactly the same principles. Okay. So what are the tests that we typically use to test for independence? This is when things got, had to get into kind of the back end of the recorded lecture, but I'll go over the most important test here, the runs test. But they're basically two types of tests, the autocorrelation test and the runs test. And you want to make sure that you know how to do a runs test by the time of the midterm. All right, so the two uniformity tests, already talked about these, chi-squared, which should be a review from 380 or 385. And the KS test, which might be new to some of you. And then after the midterm, we'll learn about how to use these more generally, but for now, we're focusing on uniformity. So if we go to that, so the chi-squared test. The chi-squared test is all about counting. It's all about binning things up and counting how many things land in each bin. So as my example chi-squared here, I've got 30 observations of what I'm hypothesizing is coming from a uniform distribution from 0 to 1, so uniform random numbers. So my hypothesized interval is from 0 to 1. On a midterm, I will just tell you, use the chi-squared test with 4 bins or 5 bins. Like I'll tell you exactly how many bins. So assume that I say that I want you to use 4 bins. So I want you to divide the interval up into 4. And so here are my 4 bins, and I'm dividing the hypothetical interval. I'm not dividing the actual interval from the random numbers. I don't say, well, this thing goes from 0.01 to 0.95 or something. I say, no, what is the hypothesized interval? And so under the null hypothesis, this is randomly distributed between 0 and 1, uniformly distributed between 0 and 1. So I divide that hypothesized interval up into these 4. And then I count how many of my actual observations land in each one of those bins. So after I do that, I can see that 3 were in here, 4 were in here, 8 were in here, and 15 were in here. So I just go through and I tediously go through and I count each one of these and see how many landed in there. So now I have those, and now I need to ask, well, how many would I have expected under the null hypothesis of uniformity? Well, so I'm going to take my 30 observations, and I'm going to say if they were uniformly distributed, then on average, if I distributed them across 4 bins that are equal width bins, then 30 divided by 4, I should get on average 7.5 in each bin. Now this is where I need to do my check to see if I can keep using the chi-squared test. If this number here, if this expected number, not the observed number, if this expected number is less than 5, then we can't use a chi-squared test. We have to use another test, like a KS test, or we have to make modifications to the chi-squared test. This like Yates correction for continuity, for example. And we'll talk all about that after the midterm. But for now, all you need to know is that the expected number here has to be at least 5 or greater in order for you to use a chi-squared test. If it's less than 5, the assumptions that make the chi-squared test break down, and the chi-squared test fails to be a useful statistical test. All right, so then we calculate the chi-squared statistic, and this is just a formula. It looks funny because it looks like the units are wrong. Like it really looks like the denominator should be squared as well. We will talk about where this formula comes from after the midterm. So just keep in mind that this is the right formula. It's squared in the numerator and not squared in the denominator. And it's just the differences between the observed number for each bin and the expected number for each bin squared divided by the expected number, and all those things added up together. And that gives you a number. This number, you can view this as the distance from the null expectation. The distance, our distribution that we expected at the null was uniformly distributed. And this, if this is a large number, then we have non-uniformity. If it is a small number, then that means it is close to the uniform distribution. And the real question is, how close does it need to be for us to be okay with it and to conclude that we don't have enough evidence to reject the null? And that's what we have to look in the back, the tables for. And so we look in the back of our chi-squared tables, and I will provide you all of these tables on a midterm. And these tables have a degree of freedom column, which for a chi-squared test is your number of bins minus 1. So it's 3 in this case. And then I'll give you a level of significance, alpha. And that significance level for 0.05, that's the standard one here. Then for 3 degrees of freedom and 0.05, then we're saying that the most you can be away from your null hypothesis before you reject the null hypothesis is a chi-squared distance of 7.81. In this case, 11.8 is much greater than 7.81. And so that 11.8 is going to tell us that this is, we have sufficient evidence to conclude that we reject the null hypothesis of uniformity. And we're saying that this random number generator is not generating numbers that are consistent with a uniform random number generator. So there's something wrong with this random number generator. There was a question in the chat, what is the null hypothesis for chi-squared tests? So for a generic chi-squared test, the null hypothesis is something like you have 2 populations that are equivalent in distribution. For this application of the chi-squared test, the null hypothesis is that the numbers drawn were drawn from a uniform distribution. And so I guess I could put that in the chat if it's easier for me to write that there, is that the null hypothesis is that the numbers are drawn from a uniform distribution, specifically uniform distribution between 0 and 1. And so if we reject the null, we reject uniformity. There was a question, could I repeat what it means for the chi-squared to be large or small? The number, the chi-squared number, so I'll put this in the chat too, the chi-squared statistic is a distance from the null expectation. Or you can say the chi-squared statistic is a distance from the null distribution, which in this case is uniformity. And so if it is a large number, then that means you're very far from uniform. And so, and there's another great question in the chat. And so if it is a large number, you're very far from uniform, you have lots of reason to reject uniformity. If it is a small number, it is still possible that we could get a small number for this and not be uniform. Like if we just had 5 samples, it's really hard for me to get enough evidence to reject uniformity if you only give me 5 samples. A lot of distributions will give me 5 samples that look just like a uniform distribution would if I asked a uniform distribution for 5 samples. So you can't always accept uniformity. You can almost never accept a null, although we will talk about statistical power after the midterm, when it is safer to accept than other times, but you can clearly reject. So there was a question here, does adding more bins increase our accuracy? Adding more bins is, what adding more bins does is it allows you, it makes the test more powerful in that you can now focus on smaller regions where you would still expect uniformity. If you only had 1 bin, then you know that all 30 numbers will fall into that 1 bin, because that 1 bin will be everything from 0 to 1. So unless it's a really, really bad mock of a random number generator and numbers fall outside the interval from 0 to 1, all of your numbers will be from between 0 and 1, which basically means any distribution that generates 0 to 1 will not be distinguishable. So the more bins you add, the more ability you have to distinguish across distributions, because the chunkier you make your bins, you kind of blur out differences. And so you might have a uniform distribution that looks like a boxcar, but there might be distributions which maybe are low and then high and then low and then high, and they look more like a sawtooth. And if you use chunky bins, then if those chunky bins kind of go over a whole tooth of the sawtooth, then it may look uniform at that point. So it's always good to have as many bins as possible. But the more bins you have, you may not be able to meet that criteria that you need to have an expected number of 5 or more. So in the homework, I think the last homework, the goal was to make as many bins as possible, or maybe that, I'm sorry, I'm getting ahead. There will be a homework after the midterm where you'll have to do a chi-squared for a more general distribution. And the goal there will be to make as many bins as possible where you still can meet this criteria of 5 or more in expected value. So it's a trade-off. You want to make them large, a large number of bins, but you can't make them too large because of this criteria. And so yes, if you have more bins, you need a larger sample size. Exactly. I like the way this is said in the chat. More bins requires a larger sample size, since each bin needs at least 5 values. I want to say, just to be clear on that, each bin needs an expected number of 5 values. The observed numbers, it doesn't matter what those could be. It could be all the way down to 0. But the expected number for each bin needs to be at least 5. And so you divide the number of observation you had by the number of bins, and that gives you the expected number, and that number needs to be at least 5. Okay. Any other questions about the chi-squared? If you're given count data, so if somebody just comes at you and say, I didn't give you the distribution, but here's a histogram of how things worked out. So a histogram gives you count data, the count of things that happened in each different area here. That is an indication that if you want to test, are these data consistent with a distribution? Whenever you hear count, you should hear chi-squared. That should pop up immediately. And a data scientist's head or a scientist's head, count. Whenever you hear the word count, your head should immediately go towards chi-squared. And then it should go to alternatives to chi-squared, like Fisher's exact and things like that that we'll talk about after the midterm. But the first place it should go is chi-squared. Count, chi-squared. They both start with a C. Okay. All right, so those are excellent questions. Any other questions about the chi-squared? All right, so now we've talked so much about these expected values. The expected bins have to be 5 or more. What happens when you can't get 5 or more in expected? Well, then there's another test, the Kolmogorov-Smirnov test. Now, this test traditionally has been difficult to calculate for large numbers of samples, but it works great for small numbers of samples. It has high statistical power, so it works really well for small numbers of samples. And so when you can't use a chi-squared test, it's the perfect time to use a Kolmogorov-Smirnov test. And so you've had practice at this. The idea here is I give you a certain number of random numbers, you sort them, as in the middle row here. And then what you're basically looking for is what interval would you expect that to fall into if these were uniformly distributed? And so if I have 5 numbers and they were uniformly distributed, I would expect the first number to fall in the interval from 0 to 0.2. In the second one, I would expect it to fall into the interval from 0.2 to 0.4 and so on. So like this fourth number, I would have expected it to fall in the interval from 0.6 to 0.8, but it actually looks like it was a little higher than expected. So that's not necessarily outlaws this from being a uniformly distributed sequence here. It just means it's a deviation from what I expected. And so what you're doing in each column is you're basically measuring the distance from the intervals that you expected these points to fall in if they were uniformly distributed. And so the first row is effectively the distance from the top of the interval, and the second row is the distance from the bottom of the interval. And you can skip things when they're negative because you're looking for the highest number, not the lowest number. And so in this case, we see that the highest distance with the top is 0.26, and the highest distance from the bottom is that 0.21 that I pointed out over here. So this 0.26, what this is indicating is I expected this to be from 0.2 to 0.4, but it was too low. And so that's what this 0.26 is indicating, that it was low. And so I look at all of these numbers and I choose the maximum, in which case it's 0.26. And then there is a table, just like the chi-squared table. Now, before I get to the table, again, I want to go, yeah, I will get into what I is here in a second. So, well, yeah, so I is just the number of the sample. And so I gave you 5 samples, and they might have been in a different order, and you sort them. And so this I is the index in the sorting. So R1 is the random number that I gave you in the lowest position in the sort order. R2 is the random number I gave you in the second lowest position in the sort order, and so on. So this is 1, 2, 3, 4, 5. And if you use those indices, then this I over N, well, this tells me that I had 5 samples. And so this is this right here, 1 divided by 5. This is 2 divided by 5, 3 divided by 5, 4 divided by 5, 5 divided by 5. So the I is just the index in the ordering after you've sorted the numbers. And then this maximal distance here, this again can be viewed as a distance from the hypothetical distribution. The hypothetical distribution, the way we've applied it here, is the uniform distribution. The larger that number, the farther you are away from uniformity. So the question is, how far can you be for us to still be able to call you maybe uniformity? So what's going to be too far away? And that's what the table tells us. So for a KS test, the degrees of freedom is exactly the number of samples. So the number of, it's not bins, it's the number of samples. In this case, it's 5. And the significance level I would give you, and it would be, you know, in this case, 0.05, that's the common one. And so we look and we see that there is a critical value, a critical distance of 0.565, which means that if this number is greater than 0.565, then we conclude with a significance level of 0.05 that these are not uniformly distributed numbers. This is under that. So all that tells us we don't have enough evidence to reject. But I can tell you the KS test is so good at what it does that it is rare for, even for small numbers of samples, for the KS test to fail to reject a distribution that is not uniform. And we will talk more about that after the midterm, what I mean by that. But basically the KS test works for even very small numbers of samples. Still, I don't ever want you to say we accept the hypothesis of uniformity, but I do want you to say things like we failed to reject uniformity with a KS test, and so, you know, we do not have evidence to suggest that this is a bad random number generator or something like that. There's a question, is there a generally agreed upon sample size that this test no longer becomes accurate, or do you simply use this test when the chi-square cannot be used? That's an excellent question. After the midterm, we will talk about the topic of statistical power, which is not, which actually has a rigorous meaning. And doing a so-called power analysis answers exactly the question that you just asked. And so it's, so far, we've just had these kind of heuristics like, oh, you should have at least 10 samples. Well, it turns out that professionals don't just use that. I mean, they might start with that. But when you really want to do a rigorous design of experiments, there actually are ways to tell you exactly how many samples you need for you to start trusting a result like this. So there is a way for me to put in these random numbers and say, for the amount of variance that I measure in these random numbers, I need at least 10 samples to not be rejected for me to really say that uniformity is good here. So, so that's something we'll get to afterwards. And so, I guess my big answer right now is it depends. If these random numbers had or I guess I would say if these differences here had a lot of variance, then I might need a lot of samples. But if these differences didn't have much variance, I might not need as many samples. And that's what the power analysis will tell us how to do. And we will do that after the midterm. All right, any other questions about those two tests for uniformity? Make sure you know how to do both of those tests for uniformity. Okay, excellent questions, by the way, in the chat. Thank you for those. Those are really great. All right, so the other test that we need to do is a test for independence. And so in the video, I kind of mentioned that the kind of classic way to test for independence is to use this so-called autocorrelation test. And this is a test which basically says, if I have a string of samples and I shift that string of samples by a certain shift size, which we call a lag, then how correlated is my unshifted version with my shifted version? If you do that for every possible lag, then you can use those correlation coefficients, the so-called autocorrelation, to determine if there's independence in your sample. And if it's truly independent, then the only time you should be able to predict what's coming next is when you have a lag of 0. In other words, you know, the current data only can predict the current data. If you have, if at other lags you have significant correlations, then there is a lack of independence. Now, the problem with these autocorrelation tests, which I'm not asking you to do, I just want you to be familiar, you need to know the word autocorrelation. So autocorrelation characterizes the correlations between one sample in a sequence and other samples later in the sequence. It's correlation with itself, autocorrelation, self-correlation. So you should know the word and be able to recognize it, but, and we will use it later on after the midterm and for slightly other reasons. But it's really hard to test for independence because you have to do all these different lag calculations. We would like more of a kind of a one-shot test. And so we introduced the runs tests, which are great tests for testing for independence. there are a bunch of different types of runs tests. Depending on who you take stochastic simulation with, some people will teach you like a runs up and down test. Previous versions of this class with other instructors have done a runs up and down test. I don't teach the runs up and down test because I think the runs above and below test is an easier test to wrap your head around and an easier test to execute. But I have had students finding midterms for old professors learn the runs up and down test on their own. And when I ask them to do a runs above and below test on my midterm, they'll do the runs up and down test. They do it perfectly, but they get exactly the wrong answer because it was the wrong test, and I can't give them any credit. So back when there was partial credit, when I was grading everything by hand and it wasn't, just with multiple choice, I couldn't even give them partial credit because it was just the wrong test. So be careful there. Is it like if you are studying or whatever, make sure you study my materials, which use the runs above and below test, which is the right test to use. But if you go into like MATLAB, there's a runs test command. Likewise, you can find a similar runs test in R and whatever, where you basically can tell it what type of runs test you want to run, above and below, up and down, etc., and it'll do that. So how do these tests work? So here's a simple example. I'm going to take my 30 numbers again. And I want to know, I don't care whether they're uniform or not, but I do care whether they're independent. So what I'm going to do is I'm going to calculate the mean of these numbers. I won't have you calculate the mean of 30 numbers on a midterm. If I give you 30 numbers on a midterm, I will also give you the mean of those numbers. As a hint, if I give you the mean of those numbers, it might mean that you should be considering using this test. So sometimes people ask me for the mean, and it's like, well, if you think you need the mean and I didn't give you the mean, maybe you might be using the wrong test. But so I'll probably give you the mean if I gave you this many numbers to look through. So you calculate the mean of all of these numbers, the arithmetic mean, and then you replace every number with whether it is above the mean or below the mean. So these first two numbers are below the mean of 0.67, and this last one is above. So down here, this becomes 001. So it was these three numbers, and it's now 001, where 0 is below the mean and 1 is above the mean. And so now I basically have turned a string of numbers between 0 and 1 into coin tosses that are either heads or tails. And what I really want to ask is this consistent with an independent coin, with a coin where every toss is independent of the previous toss? It can still be a weighted coin. It doesn't have to be a uniform coin. It doesn't have to be a fair coin, but is it at least an independent coin where the previous flips do not predict the next flips? So in order for me to do that, I need to count how many above and below. So the number, each one, those are above the mean, and 0 are below the mean. And so the NA and NB are the number above the mean and below the mean. And this allows me to account for any weightedness of the coin flip. Is it a fair coin? This coin isn't quite fair. It doesn't appear to be, because it gets more heads than tails. It gets 17 above, but only 13 below. But that's fine. I just adjust my expectations to deal with it not being a fair coin. Then I count the number of runs. What is a run? A run is a contiguous group of outcomes that are the same. So 0, 0 is a run. A single 1 is a run. Another 0, 0 is a run. This long string of ones is a single run. I can break those up. So here's that same output across the top. And I've now broken them up into all of their runs. And there are 19 runs here. So you can see I took the 0, 0, they come down, the 1 comes down, these 0, 0s comes down. You can count out all 19 of these runs. So I got a run of 19. So then I need to ask, from a statistical point of view, if I had an unfair coin that had this level of bias, where 18 head or whatever, 17 heads and 13 tails, what would the distribution of runs be if I were to run this 30 flip experiment over and over and over again? And it turns out I can model that. And I know that it's going to be normally distributed with a mean of 15.7 and a variance, notice this is a variance formula, of about 7. And so that gives me a bell curve of what I would expect if my null hypothesis of independence is true. So under the null, this is the distribution of runs. So now I need to ask, does this number of runs, how likely would it occur under that null hypothesis? And for that, I can just use a z-test, just calculate a z-score, because I know that I have this distribution, this normal distribution, as my null expectation. So my z-score is just going to take the number of runs I observed minus the expected number of runs divided by the standard deviation. And be careful about this. That's the square root of this variance. So here I calculate the statistic this way, and then I get my z statistic. And so now I just need to ask, if you get a z-score of 1.2, what probability does that correspond to? What would be the probability that you would get that number or higher, you know, if looking at a standard normal? And so what I do is, because I'm interested in the two-tailed test, and I'll answer that question in a second in the chat. If I look at a two-tailed test, which we'll use these two-tailed tests, which basically means I want to test for deviations both on the high side and on the low side that are that distance away, then my alpha of 0.05 is going to mean that I need to look into my z-table with at the alpha divided by 2 level. So I look at it at the 0.025 level. And so I see in my one-tailed table, I look at 0.025 and I find a critical value of 1.96. And you use these z-tables so often and because we use this significance level so often, that that number should get burned into your head, 1.96. And so I see that this z-score is less than, and this will be an absolute, if this is negative, take the absolute value. So this z-score is less than this threshold value here. And so that tells me that I am not going to reject the hypothesis of independence. So there was a question in where did I get the equations for mu sub r and sigma squared r? Those are equations you should have on your formula sheet. Those come from if you assume a Bernoulli random variable, so a random variable that is heads or tails and has a certain probability distribution, which is going to be the number of heads divided by the total number of flips. So if you make those assumptions, we can then do a little bit of math, like the same sort of math maybe you'd see in 470, maybe you'd see in 385, to derive the distribution of runs. So we can actually model that mathematically. And when you do that model of how many runs would you expect to get out of that coin flip, then you find out that it is normally distributed, at least for a high enough number of coin flips, it's normally distributed. And the mean is this formula and the variance is this formula. Because it's kind of outside the scope of the class, I didn't go through the derivation. If you look up the runs above and below test, you can find the derivation for that. But so for now, just take them for granted that this is the mean of a normal and this is the variance of a normal. And under the null expectation of independence, the runs test is normally distributed. The number of runs is normally distributed. And so that's, just take those formulas down. And the concept of a run, there's a question there, is just, again, so I just took my outputs here. So this is the number these are the ones below the mean and this is above the mean. So I just converted this into this sequence. And a run is a group that have the same outcome. And so if I were to then break these things up, so there, these are my outputs here. So some are below the mean and some are above the mean. See this long string where they're all above the mean? I just group all those together and that is one run. And so that's what I've done down here. That is the 6th run. So the instant it goes to 0, the run ends and we start a new run. So every time you switch state, go from heads to tails. So you're like heads, 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 tails. Well, that switch, that was the end of one run and the start of a new run. Okay. Any other questions about the runs test? All right. So we've got 15 minutes left. I want to make sure we get an example of the random variate generation like you've been doing on your homework. So I'm going to skip over some slides that are in there, but they're meant to be review. So hopefully everyone is comfortable with the linear congruential generator. make sure you know how to use a linear congruential generator. Be great to have formulas like these on your formula sheets for your midterm, and just be comfortable with doing calculations like these. Know what a modulus is, know these words. I probably won't use A, C, and M. I'll probably refer to the multiplier, the increment, and the modulus if I refer to an LCG. Know that an LCG gives you independence and gives you uniformity under the right conditions, but it has short cycle times. And the combined linear congruential generator, the CLCG, gives you longer cycle times. That's another important thing I would say you should probably know. All right, so now let's jump into the new content to close out the rest of the class, unless there's any questions about random number generation before we jump into this random variate stuff. Random number generation and testing for random numbers. Okay. All right, so jumping ahead, you've had some exposure to ARENA. You know that if you dial in now to something like the drilling process, which I think is the first problem in the lab 5, then you get a box like this and you can say, all right, I want to seize a resource for a certain amount of time. And I go down here and I set my delay. I don't even need to seize a resource for this. I just want to delay. And if I set this to expression, then I can put a mathematical expression that characterizes the distribution that I want ARENA to draw from. And it's got a bunch of ones, standard, exponential, normal, or whatever. But also, if you have a distribution that is not available to it, then you need to be able to find a way to put that formula in there. And the question, and we've already seen one way to do this. So like back when you did the Monte Carlo lab, I had you generate random numbers that were uniform, but not between 0 and 1. They were between like 2 and 4. And we learned a formula for that, like the formula you see down here circled under expression. And what I say is, how do we figure out how to write those formulas in general? If I have a distribution, how do I get it into ARENA if ARENA doesn't also already have that distribution? And that's what we're talking about today. And I've already kind of outlined the basic process of so-called inverse transform sampling, or the inverse transform technique. If you've got a CDF for a random variable, you take its inverse, which is equivalent to sort of treating the y-axis as the input to the function and the x-axis as the output. And then that function that you get from mapping the y-axis back to the x-axis gives you a way to turn uniform variation between 0 and 1 into whatever variation you want. So if I was to look back at ARENA here, there's a unif 0, 1 that I've put in here. So basically there's an expression, which is like 4 minus 2 times r plus 2. And that r is where ARENA is going to draw a random number between 0 and 1 and just plop it in there. And it's going to do that over and over and over again. And it's going to take each one of those numbers from 0 to 1 and stretch them out and shift them in order before it dumps it into this process here. And this is just generalizing that to other distributions as well. So that's what we're kind of doing here. And so where this comes from here is we're going to say that I've given you a CDF, or I've given you a PDF, and you have to derive the CDF. And so we have to solve for that CDF. And then once we solve for that CDF, we need to then invert that CDF. And once we invert that CDF, then that becomes our random variate generator. So we can then load up the input of the inverse CDF with numbers distributed between 0 and 1. And the output that comes out of the inverse CDF is going to be distributed like we want it to be distributed. That's the inverse sampling technique. So here's a simple example for an exponential. Here is a PDF for an exponential, and it's piecewise. So there's no density for outcomes less than 0. And then there is non-negative density for all outcomes greater than 0, with a concentration of density closer to the origin, closer to the axis. So I know a CDF takes this formula here, but this is piecewise. So I need to break my CDF up into 2 pieces. The first piece goes until 0. And so it's going to be the integral of this density function evaluated for x values less than 0. And the second function goes for everything greater than 0. And because it is a CDF, because it is cumulative, then this second part, and this is the key part here, has to include both a contribution of the PDF all the way up to 0, and then a contribution of the PDF from 0 on. And that lets me split up these two parts, where this top part will go in here, and this bottom part, the red part here, will go in down here. That's kind of the key thing. Most people forget this first part, which is absolutely necessary to make it work in the general case. So I plug in, so there's my 0, it goes in all these left sides, and then this one only shows up in the second row here. And then we can simplify, and there we go. Some of you might not remember how to take an integral of an exponential. I've got a little bit of a refresher there. If you want to look into it, there's a substitution. I'm not going to go into this in detail, but if you need kind of a quick refresher, then you can refer back to this slide. And there's a question, a private question in the chat. Why do we have to include that middle, that term here? For this one, it doesn't look like it's important. But if there was any density here, if we didn't include this term, then the cumulative distribution for this second row would omit all of the density from all of the previous rows. But it's cumulative, so it needs to keep adding up. And so that's why we have to add the density from the previous rows. And that may become more clear in the next example we do after I do this inverse. All right, so then we want to do the inverse. So with the inverse, all I really need to ask is I just need a way to map from 0 to 1 from the kind of the output of the CDF back to the range. So there's a question, the initial piecewise function in the PDF in this case, right? So in this case, this was initially piecewise, and that's the reason why I had to carry through the piecewise, yes. If this wasn't piecewise, we wouldn't have to worry about all this stuff. We just handle it with the one chunk. So when I invert this, I just need to then figure out, well, my CDF maps from my range to 0 to 1. So what I need to do is to figure out for the inverse CDF, it's going to map from 0 to 1 to some a bit of the range. It might skip over some of it because that doesn't actually have any density. And so I need to kind of figure out, if I were to go from 0 to 1 on the y-axis of the CDF, what spots of the x-axis are going to get a nice shadow on them from that image of you can view the y-axis kind of being light being shined in, and then it gets kind of like a prism, gets then like reflected onto the x-axis by the CDF. And then those little halos of light that are on that x-axis, those are the portions of the CDF that you care about. And in reality, they're just the portions that have non-zero density. So wherever you go to the density and it has a non-zero density, that is probably a row in your piecewise derivations that you need to focus on. So for this one, 0 to 1, there's only density in this upper portion here. So that's the only portion I care about here. So I just set R equal to my CDF, and then I solve for X, and that's just what I did there. And the right-hand side of that process becomes my inverse CDF, otherwise known as a quantile function. And then that is what I can use to then generate my random numbers. There's a trick that the book mentions where you can replace 1 minus R with R, and you get a variate that's slightly more efficient. Note that trick, but for ease of grading, never use it on a graded assignment unless I ask you to use it. So that way the grader has got to look for other things to grade for. So if you get a 1 minus R, just leave it as 1 minus R. But know that in reality, to make things more efficient, it's common that whenever you see a 1 minus R, you replace it with an R. Because anything that's uniformly distributed, 1 minus that will also be uniformly distributed when it's between 0 and 1. So that's the optimization I make there. All right, only a couple minutes left. So I just want to make sure we see the triangular version. So the triangular version is a more complicated density function. So it doesn't have density below the minimum or above the maximum, but it has a density that's rising up to the mode and then falling after that. And so this is the PDF, and we want to generate this CDF. And so in this case, we do the same process. So we've got 4 pieces. So we're going to have 4 pieces of the CDF. So they correspond, all of these here correspond to all of these things here. But note that I don't discard the previous pieces, I keep them around. So this goes from negative infinity to A and A to X. So this middle piece here, which corresponds to this piece here, has got the contribution from the first row from negative infinity to A, plus the contribution from the second row, which is from A to X. So I can fill in all of these functions and then do the integrations as I fill in, and that's all that I do here. And so I just stepped through a couple of slides where I did all of that, and then I can simplify. And if I did everything right, then I should have a 0 on this top part, and I should have a 1 down here. And these should be rising from this point all the way up to this point. So I get this non-decreasing shape, which matches the S curve that I was expecting. If you do this and you find you got yourself something greater than 1 or less than 1 here, you get a 0 or a 2.5 or whatever, then you've done something wrong that probably has to do with how you've carried through these integrations from the previous pieces that I've tried to color code here for each one of these rows. And so that's our triangular distribution. To invert it, that's another kind of interesting thing where, again, we're only going to focus on the pieces that had positive density. And so those are going to be these middle 2 branches. They eat up all of the density. So that's where we're going to focus on for our inverse. And so we say that, you know, if our PDF or our CDF maps from A to B to 0 to 1, what does the inverse do? Well, the inverse is going to map from 0 to 1 to some range, A to C, and then from C to B to that other range. And so we can see by looking at this CDF that from 0 to this constant maps to the range values A to C, and from that constant to this value, that maps to the range values C to B. And so with that, we now know what values to use for our R values and our X values when taking our piecewise inverses. So we can piecewise inverse, take the inverse of this top piece, and that'll be for X values from A to C, or that'll be from R values from 0 to this constant, and likewise for down here. And so you can then do that piecewise inverse for these 2 pieces, and that's all that I go through here. So I say that I'm going to set R equal to this from A between these values. I'm going to set R equal to this thing from X between these values. And if I do those inverses, then I go down through here and I'm going to get this chunk down here. And then I need to make sure that I set these ranges correctly. And I got these numbers just by plugging in these bounds into these pieces. So if I plug an A into this thing, I'm going to get a 0. If I plug a C into this thing, I'm going to get C minus A over B minus A. If I plug a C into this thing, I'm going to get C minus A over B minus A. If I plug a B into this thing, I'm going to get 1. And so that is how you get those there, which I went backwards by accident on the scroll wheel. The only other tricky thing in the last minute here that I want to point out is that because we took a square root, we had to make sure we chose the signs here so that the range here was in the proper range. I had a choice of plus or minus for both of these square roots. I chose the plus for this one because I know that for this piece of the piecewise function, those outcomes should be between A and C. I chose a minus for this one because I know for those outcomes, those should become between C and B. And so sometimes you'll choose plus, sometimes you'll choose minus. You choose the ones that make sure that your outcomes fall within the expected range. All right, so that's kind of where I want to stop. The punchline to all the rest of the slides, which are kind of bonus slides here, is that rather than doing all these derivations yourself, you can look up tables where if you Google for quantile function, you'll find where people have already derived the inverse CDFs for a wide range of distributions. So you already have them available for your use. I also mentioned in the rest of these slides that for some distributions, like the normal distribution, there actually is not an analytical form for an inverse CDF. And so special tricks have to be done to be able to sample from the normal distribution. That's outside of the bounds of this class to discuss those, but just for bonus, I have put one example of how to sample from the normal distribution in these slides for those who are interested. You can follow along in these slides and you'll find an example of that there. But I am just focused on the inverse transform technique in this class. That's all you'll be tested over. So with that, let me stop there. I'll give you an attendance exercise. I guess I should also mention that this inverse transform technique also applies for discrete random variables in the natural way. So I am going to recommend that, that you kind of look ahead to that. And if we like, I can actually start the review session with the application of this to discrete random variables, because you'll definitely need to know that for your midterm as well. So maybe I'll just plan on doing that. I'll start the review session on Thursday with discrete random variables, and then otherwise it'll be all your questions. So with that, I'll put this, the attendance question today, and here the URL I'll put in the chat. And this attendance question is I'll say so try to think back. So the question is, if you wanted to change the seed of a random number stream in ARENA, where would you go to find the seeds element? So there is a seed block that you can draw into ARENA, and if you drill into it, you can then adjust the seeds. And so all I'm asking for your attendance question today, and again, this is not graded for correctness, it's graded for coherence and completion, is where would you find that block? So is it in the run setup, or where is it? So where do you find, where do you adjust the seeds in ARENA? And otherwise, I can stick around for a couple of minutes if there are any other questions. If not, then you know, Thursday is the review session for the midterm. So so that's the plan. So if you don't have any other questions, you can feel free to drop off. Okay, looks like people are heading out. All right, well then I will end the meeting and see everybody on Thursday. Have a good week.